My name is Courtney Sigloh, and I've had the opportunity of partnering with Salazar Architects on expanding the scope of carbon accounting for projects. My internship included three main tasks. The first was tracking and reporting all relevant projects for AIA DDX. This included running energy models for each project using the Cove tool. Next, a research-based task was investigating life cycle analysis and embodied carbon tracking. Salazar wanted a tool and a process to begin recording embodied carbon data on projects. Lastly, I had the exciting task of making an infographic for communicating the embodied carbon research with clients. So, some quick context. Salazar signed the 2030 Challenge in 2019, and this is their second reporting year. 14 projects were reported this year, including new construction and renovated works, all of which had appropriate energy models, and one project reported on embodied carbon data, a direct result of this internship. 4 of the 14 projects took a deeper dive into how best to integrate Cove tool into the design process. Full use was made of the optimization feature to run comparisons, and then some recon efforts went towards figuring out the best way to track and model renovated projects. I'll be walking through some of these more project-specific results with the team later this week, but for our time today, I want to hone in on the embodied carbon research and discoveries that were made. Very quickly, embodied carbon is the total carbon emissions from building products, their transport, and end of life. And it's important because as we continue to design more operationally efficient projects, the embodied carbon emissions will hold a greater proportion of influence in projects. It is anticipated that it will be responsible for 72% of the carbon emissions associated with new building construction. The first step to successfully calculating embodied carbon is selecting an appropriate tool. After investigating a few promising options, we decided to use the Tally application by Kieran Timberlake. The tool allows you to run assembly comparisons for more focused embodied carbon research, but also whole building life cycle assessments. And it's all made easier with integration into Revit. I ran a handful of assembly comparisons using the design options tool in Tally, 4 of which I fully documented and analyzed, one of which I'll be sharing with you today. We chose to focus on global warming potential, or GWP, for our performance metric throughout the comparisons, although Tally does show 7 different sustainability metrics that you could choose from. This comparison is looking at typical exterior wall assemblies used by Salazar, and it mainly focuses on the change in insulation between them. So option 1 here shows mineral wool within the wall cavity. Option 2 shows blown cellulose within the wall cavity. And option 3 shows an exterior rigid insulation as well as insulation within the wall. You can see from this chart that option 2, with blown cellulose, outperformed both alternatives with respect to global warming potential. However, this begins to bring into question whether or not it is the most efficient option. Some may argue that option 3 would perform the best thermally and with respect to operational energy and operational carbon. We'll come back to this question of embodied carbon versus operational carbon. Nonetheless, we did learn quite a lot about the embodied carbon footprint associated with these 2 different insulations and their respective performance. So you can see here to the left that 5.5 inches of mineral wool insulation performs at a value of R21, but with almost 6 times more embodied carbon than 7.25 inches of blown cellulose at an R value of 26. Although their R values are relatively similar, the embodied carbon impact changes tremendously. Blown cellulose becomes a far better sustainability decision with respect to embodied carbon. So after testing a few comparisons with the design tool, we progressed to running a whole life cycle analysis for a current project. The Gold Crest project was selected. It's 82,000 square feet with 75 affordable housing units, a great benchmark for Salazar as they begin tracking embodied carbon. Right from the start with this chart, you can see that the products we choose have the greatest impact on embodied carbon, followed by their maintenance. That means we need durable, carbon-smart materials. Another big question that arose from a more specific material investigation relates to biogenic carbon. Biogenic carbon is the carbon sequestered through the use of certain natural materials, namely wood. There is a lot of debate right now as to whether or not it is appropriate to include biogenic carbon. You can see that from these charts that the inclusion or exclusion of biogenic carbon has a significant impact on the whole building life cycle analysis. When it wasn't accounted for, wood had the largest impact on the global warming potential. When it was included, concrete and finishes show the greatest impact on the project. So whether or not it is included shows way too much variation to not be standardized. As embodied carbon tracking continues to grow, there needs to be a consistent method across firms, or there might be a possibility for very different reporting results. One last insight that was gained from this whole building analysis can be seen in this graph here. So gypsum wallboard accounts for 26% of the project's total embodied carbon. That's a lot. It's more than the typical offender concrete. And this is concerning because there aren't many alternatives to gypsum, and it's used everywhere throughout a multifamily housing project. So we can spec lighter and thinner gypsum in our projects, which will bring about a marginal improvement. But I think I see an opportunity for more research and innovation to be done here. Finally, Tally helps provide embodied carbon data relative to the project's square feet. So this allows us to track projects against each other and then report data to places like AIA DDX. So the final task was creating an infographic to engage clients on carbon-related sustainability conversations early on. This drawing provides a breakdown of design decisions by project component with respect to embodied carbon, cost, and difficulty. Think of it as a menu of sorts. This provided a helpful tool for synthesizing all the information and research I had done with respect to embodied carbon, and hopefully provides a helpful tool for future conversations between Salazar and their clients. So, what's next? Through my 3 tasks, I looked at optimizing and tracking operational carbon through energy modeling. And then I looked at analyzing and reporting on embodied carbon through Tally. The trouble is, how do we quantify and track these things alongside each other? Up until this point, carbon operationally has been prioritized in building sustainability. Policy and codes have contributed towards a collective effort in reducing buildings' EUI. Now we must turn our attention towards embodied carbon. And as architects, we will be the most significant initiators. We have control over the materials that we choose, and we have the responsibility to choose carbon-smart materials. Once embodied carbon has been poured into our projects, concrete pun intended, there is no going back. We can upgrade building systems, but we cannot retrofit away the embodied carbon already expended. So, when it comes to holistic embodied carbon accounting, or holistic carbon accounting, is the best building no building? Is our best foot forward using an existing structure? How do you quantify the trade-off between a less operationally efficient old building and a new net zero building? I will leave you with these questions. Thank you so much for your time and sticking it out until the end. Thank you to Salazar and Energy Trust of Oregon. And now I believe we're turning it over to you for your questions.